Okay, Assalamualaikum warahmatullahi wabarakatuh. This is recording lecture for chapter 9, stress transformation. So here we'll cover 9.1, 9.2, 3 and 4, right? 9.1 is plane stress transformation. 9.2, general equations of plane stress transformation. 9.3 is principal stresses and maximum inflation stress. And 9.4, Morse circle for plane stress. Basically for Morse circle, actually there is another method, alternative method for 9.2 and 9.3. And before you go to this chapter 9, stress transformation, you need to understand chapter 8, right? If you still do not understand how to find these resultant loadings and I mean the state of stress, define the state of stress for combined loadings, I think you better go back to chapter 8 first. Okay. Then so let's start with plane stress transformation. So you have seen this before, the general state of stress here, right? Where you have the sigma x, sigma y, and sigma z, of course in 3D, and then you have this the three other components: tau xy, tau xz, and tau yz, right? And then if you simplify further, for instance, you analyze in single plane of plane stress, then you can eliminate. Actually, there is a meaning for this. Actually, for plane stress, that you will have sigma z, not sigma z is zero because it's very thin. For instance, in plane stress, the the plane is the geometry is thin, so you say that the sigma z is zero. So you can reduce this to become sigma x, sigma y, and tau xy. Of course, there is a concept we have for that, but it's beyond the scope of this chapter, right? And then what you can see is from these three degenerate state of stress, you can reduce into plane stress of sigma x, sigma y, and tau xy only, right? And then what you have is for this general state of plane stress, you have only sigma x, right, in the x direction, sigma y in the y direction, and tau xy in xy direction, right? And then having said that, this is this plane, okay, this element, it follows the original x and y configuration, right? What happens if you rotate that one? I mean, if you say that, okay, instead of x, y like this, you rotate it like this or like this. I mean, with an angle. So what happened? So this is what you're going to do in this chapter, okay? Whatever you have done previously up to chapter 8, right? That one actually you follow the XY, XYZ or XY in this case for plane configuration of the one uh, that you define, you predefine before you solve that, right? But actually, this element don't necessarily have to follow XY. It can be rotated. That's what it means here. It can be rotated by this angle theta, all right? So if you rotate, of course here, if having said that, if you have x, y like this, then theta is zero, okay? But you can rotate that and you have the same, actually, the same state of stress. It's just the values will be different. But this and this, the rotated one, is the same actually. That's their equivalent, right? I'm not saying the values are the same. Sigma x prime, sigma y prime won't be the same. Tau x prime, y prime won't be the same. But the thing is, the state is the same. They are equivalent state, right? Why I said that? Because later on you will see why this is important, right? So okay, this from this slide, the most important thing is that you realize this element can be rotated with angle theta, right? Why you want to rotate? You will see that later on. Okay, so we go to the next one, next topic, which is general equations of plane stress transformation. So before we do that, please understand this sign convention. Remember, normal stress, positive outwards, okay, negative inwards, okay. While positive shear stress, like this one, tau xy will for the right hand face, okay, of the element, it will be positive going up. If it goes down for that face, it will be negative. So we will do this, right? So this is the positive sign convention, right? Even if and the rotation, okay, if you follow xy, so if you do the rotation, you follow the right hand rule, so the theta will be positive anti-clockwise. Okay, anti-clockwise will be positive theta, right? So this is what I explained just now. Okay, if you rotate anti-clockwise theta, then it becomes a positive angle. If it is clockwise, then it is negative angle, right? And then remember the normal stresses will be positive going upwards, inwards. I mean compressive will be negative, and tau xy will be positive if the right hand side, okay, going up, right? Right, so this is how we derive this stuff, general equations of plane stress transformation. So how you derive it is you cut it, okay, you cut here, and then you draw the forces, right? All these are forces, and then from these forces you do the summation of x prime. Okay, x prime now it is the theta angle, right? Equals to 0, fy prime equals 0, and then you solve this, then you will come out with these two these two things. One is this tau x, sigma x prime and tau x prime y prime. Okay, what are they? They are basically this sigma x prime, right? And tau x prime here, x prime y prime. Sorry. When your angle, your plane, your element has been tilted to sigma x, which is theta clockwise from original x. Okay, what is this sigma y prime? This is for another one which is here. Okay, this sigma y prime is actually, if you understand this, actually this is from theta plus 90, isn't it? Theta plus 90. Theta from x to y prime, isn't it? From x to y prime. So theta plus 90. So this one, sigma y prime here, this equation, right? This is actually from sigma x, from this sigma x prime. But the theta here, you put theta plus 90. So it becomes like this. Okay. But again, the most important thing is these two actually. If you understand these two, that's more than enough. Sigma x prime, tau x prime, y prime. Right? Okay, now we go to the example that we want to rotate. I mean, using this method, right? So, for instance, you have this airplane fuselage, okay? And then you have a point over here, and then you take out this point, you represent this point as the plane stress, okay? And then you have this 80 megapascal, okay, and 50 megapascal and 25 megapascal. So from here, you should realize by now that, okay, by now it's not there. But if you use the first method, okay, you cut, because the question asks you to represent the state of stress, the same element, oriented 30 degree clockwise. So you rotate this clockwise, okay, minus 30 degree, isn't it? So what you have to do is you have to cut 30 degree, right? This 30 degree. When you cut this and then you follow those methods, then you will end up with your sigma x prime as this and sigma tau x prime y prime as this. And of course, when you do the other one, you will have your minus 25 megapascal. All right, and then you express it as this state. You see, you rotate it 30 degree clockwise, then the sigma x prime, sigma y prime, and tau x prime y prime will be different, but they are equivalent with the one that you saw previously, which was this, right? Now we go to the one which is simpler, which is we use the equation, right? We don't have to cut. So, for instance, here you have the element, right? And then you have this 80 megapascal, you have 50, you have 25. So you need to interpret here. What is this 80? What is this 50? And what is this 25? So you have to understand x, your x, right, going to the right, y going up, isn't it? So your sigma x is this, but the value is negative, right? Your sigma y is this, but the value is and the value is positive. And your tau xy, the shear stress is this, and the value is negative. Okay, you have to see this. So that's why your sigma x equals to minus 80, right? Compressive. Sigma y equals to 50, tension. Tau xy equal to minus 25. Why? You see the one which is on the right hand side, the right hand face, it is going down. So it is minus 25 megapascal, right? And then the angle is, okay, look at the question. You rotate it 30-degree clockwise. So you rotate 30-degree clockwise, it means the angle is, angle theta is minus 30. Okay, why minus? Because counterclockwise, anti-clockwise is positive, clockwise is negative. Right? So you in order to do this, you want to find the, if you rotate 30-degree clockwise, what happened to the state of stress? So the first one is you do this sigma x prime, right? Go back to the equation. Where is the equation? This equation, right? Then you put the values sigma x, sigma y, tau xy, theta minus 30. Okay, if you put it here, then it will be different, it will be wrong. All right, and then you will end up with your sigma x prime equals to minus 25.8 megapascal. Simple, isn't it? And then for tau x prime y prime, okay, you go back to your equation, this tau x prime y prime, you put into the equation of this, you put sigma x, sigma y, and tau, of course tau xy as well, and then you put the theta of minus 30, will end up with your tau x prime, y prime as minus 68.5. Minus 68.8 megapascal. So you'll see what happened here. So here, what happened is, from, okay, this element, from x, you rotate it to x prime, isn't it? That's why you have this sigma x prime of, okay? You rotate it minus 30 degree, why minus? Again, because it's clockwise, isn't it? And then what happened is that, on that surface, this sigma x prime, when you rotate it minus 30 degree, you will have your sigma x prime and tau x prime y prime, okay? Which is this and this, okay? This is your sigma x prime, right? Which is minus 25, right? And tau x prime y prime here is minus 68. That's why here it goes down. See, this one, it goes down. On that surface, on that face, going up positive, going down negative. Forget the rest. I mean, those are complementary, but I'm talking about this surface. Okay, because we are focusing on this x prime axis that you rotate from original x, you rotate to minus 30 degree. Okay. So what happened to the other side? Okay. So for the other side, what you have to do is, okay, now you have analyzed this surface, right? CD. Okay, this CD. Okay, for this surface, what happened to this surface? Of course, whatever you have on this CD, you have the same on this, right? Okay, so we're going to see on what happened to this BC. For this BC, you will rotate how much? You will rotate how much? You will rotate 60 degree. Why? Can you see that? Okay, this x prime and y prime, so-called y prime, is 90 degree, isn't it? So x prime to x is 30. So x to x y prime, x axis to y prime axis should be 60. So which means that this angle you rotate as positive 60. Why positive? Because it is counterclockwise. And 60 because you take the whole x prime y prime as 90 degrees, isn't it? So that's why here you have the same sigma x, sigma y, and tau xy from previous one, right? But to analyze the BC, this BC, you need to rotate it at 60 degree angle, right? So this is what you are doing. Okay, that's why I said here, though this one we call it as sigma x prime, okay, but actually, I mean, if you are unsure, then you can use the sigma y prime equation before, but actually that's not the real, the correct way, the most correct way. The most correct way is actually from x to analyze CB, surface CB, from x you rotate it 60 degree clockwise to have this axis, which is normal to face BC. Right? So you use the same equation of sigma x prime, but your theta here is 60 degree, positive 60 degree, and you will end up with sigma x prime as minus 4.15 megapascal. Right? And then for your top x prime y prime, okay, which is on this surface, CB, you will have your value as positive 68.5. Plus this one is negative, this one is positive, right? So what happened is, on this surface, you will have compression of 4.15, right? This one, isn't it? And the shear stress of 68.8 megapascal, which is this one, right? Going up, okay, going up. So now it is correct. I mean, whatever happened here and there is just the equivalent, okay? The complementary and equivalent stresses, right? Of course, you have 44.15 here, you have 4.4 here as well, compression. You have 25.8 megapascal here, you will have 28.5 megapascal here as well, right? And then the rest are complementary shear stresses.